Apple Park, where architectural innovation meets engineering excellence. As we delve deeper into the structural complexities of this iconic campus, we uncover the formidable challenges that shaped its design and construction. Going from the meticulous integration of floor-to-ceiling glass partitions to seismic considerations that defy convection, Apple Park's architectural journey is a testament to ingenuity and perseverance. We'll talk about structural challenges, void slab concept, problems of notches, and supporting girders in turn. One of the important architectural features of the office space is floor-to-ceiling glass partitions with no visible metal trim top or bottom. That necessitated the soffits being the same size as the offices so the glass could recess above the ceiling line. This made a continuous slab spanning from grid to grid an unlikely candidate. This picture depicts a typical cut-through that soffits with the offices as square off the radial grid lines and the open office space and common areas as wedge shapes in between. Another key structural challenge was created by the seismic demands of the project. While the building is spaced isolated with very small horizontal accelerations, the vertical accelerations imposed by the performance requirement was significant. The building is designed above code requirements to a performance level of minimal damage in a 2,500-year return period event. This led to vertical accelerations of 1.2 Gs on the floor slabs and the design requirement that they remain elastic and produce an insignificant amount of non-structural damage. The span lengths of up to 45 feet combined with the mass of the soffits and a floor system depth limit of 24 inches made supporting the concrete soffits a major challenge. The precast double T solution was proving to be ineffective. The 4-inch thick concrete ceilings were leading to excessive deflections while not contributing to the structural performance at all. The cast-in-place solutions were proving to be excessively heavy as well, and steel solutions were too flexible in the allotted space. From the seamless integration of floor-to-ceiling glass partitions to seismic considerations pushing the boundaries of convection, each obstacle met was an opportunity for ingenuity to shine. Seeing beyond its stunning architectural facade lies a world of structural ingenuity and meticulous design considerations. As we delve deeper, we uncover the intricate solutions devised to meet the demanding performance criteria set forth for this visionary project. The desire for the architectural ceilings to remain uncracked and for the members themselves to remain elastic in a 1.2 G vertical acceleration event, combined with the narrow envelope of acceptable deflections, led to the development of a press-dressed long span unit with a continuous bottom flange. Numerous early designs and prototypes were created. The top of the picture depicts a rendering of a double I formation. The top flanges of precast support metal decking and a concrete fill on deck diaphragm. This section was structurally effective but difficult to form and strip in the precast plant. The final shape is pictured in below. The top shows the profile of the unit with the glazing track notches at about quarter span, and the below shows the reinforcing press-dressed cross-section. The total precast cross-section allowed the ceiling surface to be utilized as a structural flange in combination with the structural stem units supporting the floor above. This created a much more effective cross-section for both strength and deflection performance. The use of press-dressing in the section kept the slabs from cracking under surface loads and the limited deflections to at the 1.2 G vertical acceleration event. Beyond its captivating exterior, meticulous design considerations and engineering ingenuity have paved the way for a structural solution that meets the stringent performance criteria of the project. Engineering is needed when it comes to design, but it does not come without challenges. It constantly demands innovation solutions. One such instance is found in the case of a specialized structure featuring 2.5-inch deep notches in its flanges. These notches, while solving a specific purpose, introduce complexities that required careful considerations and as well strategic planning. The 2.5-inch deep notches in the flanges created challenges as well. The flanges were pre-stressed with 14.5-inch diameter strands at an elevation of 2 3/4 inch above the finished surface, meaning they touched the top of the notches. Due to reduced cover, they were not considered effective for strength combinations in a fire. They were considered effective for seismic combinations and deflection considerations. The fire-resistant design relied on additional strengths and mild steel up higher in the stems with adequate cover. These notches also created a shear lag effect during press stressing that required additional hunches to get the flange press stressing forces over the notches without inducing principal axis cracking. Those showed the FE analysis of stresses in the section due to press stressing. The FE analysis of the section accurately predicted hotspots and local hourglass pattern cracking that was observed in all the prototypes of the slab section due to press stressing forces. The structural shape was improved with buttressing pyramids that allowed the compressive stresses to get over the glass track in a without these stress risers. This journey exemplifies the dynamic interplay between engineering challenges and innovative solutions, ultimately ensuring the integrity and performance of the structural design. In the realm of structural engineering, innovative solutions often arise from the interplay between creativity and practicality. One such example is the design of supporting girders for void slabs, a critical aspect of modern construction projects. Join us as we delve into the world of supporting girders and uncover the engineering marvels that underpin modern architecture. With the void slab cross-section and structural member design determined, the end supports of the void slab were all that remained to be solved. The void slabs rest on ledges of precast post-tension girders or on a continuous ledge at the shear wall lines. The support connection chosen was a trussed hanger bar, a rectangular steel bar with welded inclined rebars and that transfer the reaction into the stems of the units. The girder and wall ledges were designed for the concentrated reactions. The soffit space below the girder was shrouded with either an architectural beam cover or partition framing where walls were placed. The slanted opening of the soffit provided space for return air flow up into the as well as a place to mount lighting. These girders repeated themselves at every interior radial grid line, and at every other grid they aligned with an I-shaped core shear wall. In those occasions, the girders also had to perform as collector elements, delivering more than 400 kips of force to the shear walls. The member detailing for the remainder of the load paths became much more conventional, single-lift precast columns to weld through the girders and connected to upper columns with Type 2 splice sleeve connectors, and single-lift precast shear walls with the same Type 2 connectors. In the intricate dance of structural design, the end supports of void slabs stand as a final piece of the puzzle. Through the utilization of precast post-tension girders and innovative truss hanger bars, engineers have crafted a robust system capable of bearing substantial loads while maintaining structural integrity. This is the end of our journey for structural parts. This is our study plan we've done for the study plan of 5 weeks. And those are the study plan for the next 6 weeks. Thank you for listening.